Okay, now I'm streaming. I'm going to share the screen again. My husband says, cut off Dropbox. Yeah, I already tried that. I'm running just the bare minimum things on here that I can. Okay, now let me make sure I've got everything going again. I've got my stream, I've got my share. Are we ready? Okay, slight lag. I'll just try to talk more slowly. And hide self-view there. I don't want to look at myself. I want to look at you guys. Okay. Where the hell was I? We were talking about R matrices. That's what we were talking about. Let me see if I can get that slide pulled up. There we go. So ways of telling it that the observations from the same person should have relationships. Okay. There's three choices. One is this, what's up here right now, what's known as unstructured. Unstructured is everything gets to be what it wants. So each potential outcome has a different residual variance estimated for it. Each potential covariance between outcomes has a separate residual covariance estimated for it. So if there are three outcomes, such as in this example slide number 17, that would be three variances, three covariances. If you only have a few outcomes, this is a fine thing to do. I wouldn't bother necessarily hunting for something better. It's when you have a whole lot of outcomes that this becomes unwieldy in terms of how many separate parameters. This is the same thing as MANOVA in terms of the error structure. It's also known as the saturated model in structural equation modeling parlance. So two structures that are simpler that you may want to try to see if they fit, not worse, is on slide 18. Let's see if it will come up. There it goes. Compound symmetry heterogeneous. That one is when you have all different variances, so each outcome gets a different residual variance, but the correlation between outcomes is constrained to be the same, regardless of which outcome it is. So there's a constant correlation between outcomes from the same person, regardless of which one it is. So that cuts down on the number of covariances to be estimated. And then the third option is compound symmetry, which says that all outcomes should share the same residual variance. And so that cuts down on the number of variances to be estimated. So compound symmetry has only two parameters, one covariance across your outcomes, and one variance. It's the most restrictive. It's also known as a random intercept only model, or the univariate approach to repeated measures ANOVA. So those are the three direct ways to put dependency in your model, is just to instruct it that it needs to be there and pick your pattern and see which fits relatively best, where unstructured is the best that you can have and an absolute point of view minus 2 log likelihood, and the other two are candidates that are simpler and thus could fit worse, and your question is whether they do. Okay, so that was the three questions on formative assessments. Any questions on that? We're good? Ready to jump back into the example? Okay, let's see if I can do that for you. Here it is. And I fixed this, by the way. There were two problems with it that I noted last time. So this is the fixed version. You can download that. So I fixed the table here. So just to remind you what we're talking about here, this is my failed master's thesis data. It is the mean response time to detect changes to visual scenes of driving under 4 conditions. The changes are either low or high relevance to driving and low or high salience, like visually conspicuousness. The original structure of the data, what's known as a wide format or multivariate format, is where my mouse is right here. Can you see my happy little mouse? Okay. So in the wide format, the first table, it's one row per person. So the 4 outcomes for response time are separate columns. The first thing that we have to do to be able to fit a multivariate model of 4 outcomes is to condense them into one column. So it's like taking the row and transposing it into a single column. So the end result of the code to do that is the second table right here, and I fixed the condition. This is the one that was incorrect before. So I have an index variable for which original outcome it was. I have 2 dummy code variables to distinguish the conditions of meaningfulness, low versus high, salience, low versus high. I have response time from the 4 conditions stacked into one column here, which is just labeled response time, RT. And the natural log of it is what we're actually analyzing. And then I have a piecewise predictor of age. Yep, and now I just realized this table is broken again because I showed the first 2 rows of the younger adults, not a younger adult and an older adult. So I get to fix it for the 3rd time. Hooray. Anywho, I got the good part. So it's the code to fix the data sets to take it from wide to long is this reshape command right here. The dummy codes then are computed from the condition index that is created during the reshaping process. In SAS, there is no easy reshape command. You have to write out the transformation that you want. So this code right here creates 4 lines of data for every line that was in the original data set. So any variable that is not mentioned in the SAS code is automatically kept in the file and copied across the rows for the same person. The same is true in Stata. Any variable that's not mentioned in reshape stays in the data set that's not currently being reshaped. So I took the opportunity to create the dummy codes and the condition index in one step here. The response time column is the left side here is what it new is going to. The old, where it's coming from, is on the right-hand side. And then I dropped the old multivariate variables. That is automatically happens in Stata. It does not automatically happen in SAS. And then last but not least, a piecewise effective age. That way I can track the effect of additional years over age 65 within the older group specifically. There's no relevant variability within the younger group that is worth modeling. Okay. Any questions on the setup or the code that it takes to get your data into the right multivariate format to be able to do this? Okay. Well, let me know if you think of any. And so this is another thing that I fixed, the notation for the multivariate model. So the table now matches the notation. I've gone back and forth across ways of notating this thing, and the way that I've settled on is similar to what I do in the multi-level modeling class, but the multivariate outcomes are the second subscript. So response time, because I have 4 response times that I'm modeling simultaneously, that means I have predictors that pertain to which response time it is. That's indicated by the subscript C for condition, which of the 4. And then I also have predictors that are person-level predictors, and that's indicated by the subscript that's the I for individual. So up until this point in this class, we've only had I's, and there was 1 subscript. And so we started at beta 0 for the intercept, and then went beta 1 for the first predictor, and beta 2 for the second predictor, and so on, right? Can you hear me? Thank you, Molly. Yeah, not everybody. I've got 4 cameras on, so you guys are like my my cross section of the class here, my random sample of people. So this is a change in the notation style. So in using 2 subscripts for each level of sampling, over individuals is I, over conditions or over outcomes is the C. Beta 00 means It's the intercept both with respect to people and conditions. Beta O1 and beta O2. O is because these don't pertain to people. These are condition predictors. They distinguish which outcome is which. And so meaning whether the change is meaningful to driving, beta O1 is the first predictor with respect to which condition is which. My internet connection is unstable, it's telling me. Yeah, no shit. So is everyone's. It booted me completely in my previous class, so this is better than nothing. Beta O2 is because salience is the second predictor of which condition is which. So those are C subscript variables. Beta 3, O3, excuse me, is the third predictor of which condition is which. And it's the meaning by salience interaction. And so those four fixed effects then perfectly recreate the four possible condition means given by this 2x2 combination of low versus high for each of my condition predictors. So technically speaking, having these four fixed effects in the model is still an empty model. They're just allowing each outcome to have its own mean in the same way that each outcome has its own residual variance, and there's covariances between the outcomes from the same person. So we're starting with a mean structure for all of the models that just has this stuff in it. So this is my empty multivariate model. And then we started looking at the R matrix structure last time, as I recall, yes. Do you remember that? Yes. So we had unstructured. Everything gets to be what it wants. That's going to fit best. It takes 4 variances in my R matrix here and 6 possible covariances among the 4 outcomes. So that is obtained in Stata right here with the residuals option for unstructured, where T is the indicator that tells it how that R matrix is supposed to be organized. So condition is the index variable. It's not a predictor in the model. It's just telling it which row is which. And the analog to that in SAS is the repeated line with type equals unstructured. Person ID is the index that says which person is which. Condition is the index that says which outcome is which. In looking at the correlations among the outcomes, so that's our core right here, they looked relatively the same, and so I thought it would be reasonable to see if they needed to be 4 separate numbers, or if we could, or 6 separate numbers, excuse me, or whether we could collapse them into one. So the next model that I tried in SAS, only because it doesn't exist in Stata, is compound symmetry heterogeneous, where I changed the type to CSH, and what that does is still allow a separate residual variance for each of the 4 outcomes, but constrain the correlation between the outcomes to be the same number. So it's going from 6 covariances across the 4 conditions down to 1 correlation. So it's a savings of 5. And we do a likelihood ratio test to see if this fits not worse, because it's simpler relative to unstructured. So -2 difference in log likelihood from this model, savings of 5 parameters. This model minus the unstructured model gives us a -2 log likelihood difference of about 7, which is non-significant on 5 degrees of freedom according to a chi-square distribution. So CSH is not worse, meaning, yeah, we could just have 1 correlation instead of 6. I also tried compound symmetry homogeneous, which means further saving on the number of residual variances that's being estimated, having 1 instead of 4. But that fit significantly worse than -2 log likelihood test. So here it's CSH. So I ended up sticking with unstructured because it was this data, although that one I could have fit instead. And then I think we let off right here. So let me blow this up a little. We can capture this a little bit. No, too far. Okay. how are we doing so far? Any questions before we jump into some new stuff? My internet connection is unstable. That means I don't know if you guys are talking or not. All good in the hood. Thank you, Molly. Although that does not look much like a hood to me. It looks like a very expensive library with excellent couches, from what I understand. All right. No one else wants to talk? Can I hear from the people without pictures? Are you guys doing okay? Oh, thank you. There's one thumbs up. Okay, there's some yeses. Excellent. Okay, then we'll proceed. So here's my new model with everything in it that I could think of to put in it. So I am taking the opposite approach from what I normally do, which is to build models up. Here I'm putting in everything I possibly could to see if I can trim it down. Because if the highest order interaction is significant, I know I have to keep everything. If it's not, I know that I can release it. So there's one more thing that I need to test with respect to my R matrix. And this is something that we've only seen once this semester. It was in the count unit, the idea that you can have different residual variances as a function of individual characteristics. Given that the young people and the older adults in this sample are so different, the older adults are a lot more variable from each other, both in age and in health and sort of cognitive functioning, globally concerned. So I wanted to see whether or not they, as a group, were significantly more variable than the younger adults. So I put everything in the model that I could with respect to age. So this is allowing the younger and older groups to differ. So the first row is what we started with. That gets us the mean of each of the four conditions according to our 2x2 meaning by salience condition design. The second row picks up the main effects and interactions involving the predictor old, which is a dummy code for 0 is the younger group and 1 is the older group. So this is allowing all four condition means to differ as a function of age group. Analogously, the third line is picking up the effect of years over 65, which is a predictor that is all zeros in the younger group, so it's effectively shut off. And it picks up the number of years over 65 in the older group. So it's a slope for age that's specific to the older group. So you can think of this as a piecewise effective age where there's one piece between younger and age 65 and a second piece that picks up after 65, that's the years variable. Or you can think of years 65 as a nested effect that operates only in the old equals 1 group. So we have a main effect and then allowing each of the condition means through the two main effects and the interaction to potentially be different by years 65. So the first thing that I'm going to check here is whether or not the R matrix needs to be different by age group. So this is something new that you haven't seen yet this semester. In Stata, there is an extra line at the end of the residual statement that's by. That says, give me a separate R matrix by the variable that's in the predictor there, which is old. Politically correct, I know. The analog in SAS is the repeated line where at the very end there's group equals old. Let me see if I can make this any bigger. There we go. I am asking it in SAS to print an R matrix for what is predicted for any young person and what is predicted for any old person. And the way that SAS does this is very unhelpful. It's the order of the person in the data set that those numbers refer to. So it's printing the R matrix for the first person and for the 156th person, which is the last old person on my data set. The analogous options in Stata are these @ on the W correlation options, and that it's actually tied to person ID. So it's actually a lot easier in Stata to figure this out. So I wanted to ask it to print out what the R matrix would look like for a younger adult and for an older adult simultaneously. And I have them shown here. So it looks like, if I'm just eyeballing these things, there is a fairly different pattern of correlation. So in the younger group, there's not much of a correlation between the residuals from the same person. In the older group, there's a lot more. So if you're slow at one of these conditions, you're likely to be slower at the others in the older group, but that's not the case for the younger group. In terms of the total variability, that's relatively the same, although it looks like maybe there's a difference in the younger group in the first condition relative to the older group. So I have this -2 log likelihood that's the fit of the model, allowing two separate unstructured R matrices, one for the younger group, one for the older group. And so that then requires 10 parameters per group. And I'm going to compare that to the homogeneous version of the model, again, that has all the same fixed effects in it, but just making the R matrix to be the same again across groups. And so here's the collapsed R matrix across groups. Here's the change in fit. And there's another typo that I just caught. So -2 log likelihood difference in adding 10 parameters, meaning two different R matrices, one for young and one for old, suggests that that doesn't help the model. And again, one of the limitations of this software is that it has to be all or nothing. I can't just say, let the correlations differ between groups but keep the variances the same, or something like that, or just let this correlation differ and keep the others the same. It's all or nothing. So the whole matrix being different isn't necessary, and so I have to go with the homogeneous matrix as something that fits, not worse. And now we can look at the fixed effects. And I'll point out the last set here. So the highest order interaction between years over 65 by meaning by salience is not significant in either model. I then ran two more models that are not shown here, removing each of the interactions with years over 65 by the main effects of meaning and salience. Those remained non-significant, and so it works out that all you need with respect to years 65 is just a main effect. And so the final model that we end up with that I wanted to then try and interpret is this one right here. So again, the first line, the betas have numeric values that differ in the second subscript because they are condition variables. So the first predictor of which condition is which in terms of which response time outcome we're predicting is meaning, the second predictor is salience, and the third predictor is meaning by salience. Now note the combination of subscripts once we add the effect of old group and the interaction with these things. So beta 10 for the effect of old. It's 10 because old is the first predictor at the individual level. So that's the main effect of being in the older group versus being in the younger group. So everything else in this line that I've highlighted here starts with a 1 because all of these effects pertain to old. The interaction of meaning by old is beta 1, 1, because meaning is the first predictor at the condition level, and old is the first predictor at the individual level. The interaction of old by salience is because salience is the second predictor at the condition level, old is the first predictor, and then the last three-way interaction term here, this is beta 1, 3, because meaning by salience is the third predictor at the condition level, and old is the first predictor at the individual level. And then last but not least, the second predictor at the individual level as a main effect is years over 65. Well, that means that how old you are affects all the conditions equally within the older group. So that's the second predictor, that's beta 2O. Okay. Are you with me? Thank you for nodding. Any of that you want to hear again in terms of notation or other setup of the model? No, we're good? Ready to jump in? More fun with interaction terms. Hooray! So let me go back up to my happy little table of means as my reference point here. This right here. Happy little table of means. So there are 4 possible simple effects that I would be interested in. There's the difference between low and high meaning under the low salience condition. So if the change was hard to find, does having it be meaningful to driving make it easier to find? So the same question, but if the change is obvious, is it still helpful to have it be meaningful to driving? Does that still improve your response time? So the difference between low and high meaning in this condition and in this condition. The other way we can go is this difference. So what is the effect of salience for changes that are not relevant to driving? And what is the effect of salience for changes that are relative to driving, related to driving? And then last but not least, there's one interaction term that you can think of as either how the effect of meaning differs between low salience and high salience, or how the effect of salience differs between low meaning and high meaning. So those are 5 things that we would want to know about these 4 cells, and we might potentially want to know about age differences across each of the cells. So the way that I chose to pick this interaction apart was focusing on just what I told you, the effects of meaning and salience under each other condition within each age group. So does the same tendency for meaningfulness to change to improve response times occur in the younger adults as in the older adults? Does the same tendency for salience to improve response times occur in the older adults as in the younger adults? So the model tells us how to get the fixed effects in all of those conditions. Let's look at the Stata version because that makes it a little more explicit. So the first set of simple slopes I'm asking for are the effects of meaning. So the difference between the low meaning condition and the high meaning condition, conditional on low salience or high salience, and conditional on older adults or younger adults. So this is the effect of meaning for low salience, because that's when salience is 0, in the younger adults when old is 0. This is the effect of meaning in the high salience condition for younger adults. This is the effect of meaning in the low salience condition for older adults. And this is the effect of meaning in the high salience condition for older adults, which means the interaction term kicks in. So these estimate statements always start with what is the variable whose slope you're asking for? In this case, it's meaning. And then what is the value of the moderator variable? So salience is the moderator, age is the moderator, and salience by age is the moderator. Next set is the effect of salience as the thing that we're trying to estimate. And so in this case, meaning is the moderator, age is the moderator, and meaning and age are the moderators. So that gets me all the simple effects in terms of pairwise comparisons across my conditions. And then last but not least, because this model has a three-way interaction term, I allow the interaction of meaning by salience to differ by age group. Did you all hear that? My son is trying to break my house, in addition to kill my internet. Two-way interactions. Conditional on age group. That's what I got highlighted here. Yes. So we can see whether or not the effective meaning is enhanced in high salience in the younger adults, the effective meaning is enhanced in high salience for the older adults, or the effective salience is enhanced in high meaning. Take your pick. You can explain it either way. I've got margins here to get me means across the conditions and a picture. I did that in SAS a slightly different way. Last but not least, I don't know if you guys have seen this or not. Have you seen this thing before, this predict statement in Stata? Have we done one of these? I can't remember if we've done one of these in this class. I don't know that we would have, because this is a general linear models thing. So what predict does in Stata is add a column to your data set that you can name whatever you want. The name of it is the first word after the predict statement, so I've called it pred. And XB means that it's based on the fixed effects only. So in models with random effects, that makes a difference. So what I'm doing is generating a column of predicted response times into the data set that has the original response times. I am then asking for a correlation between the log response time that they actually have for each case and the one that's predicted by the model, which is in the column called pred, and I'm doing it for each condition separately. So what I'm generating here is the correlation between y hat and y per condition as an effect size that you can then square, and it becomes an R-square. So rather than thinking about a single R-square for the model, given that we're modeling 4 different response times, I'm asking for 4 separate R-squares. So the only terms that could contribute to the R-square are between subjects terms, individual level variables such as age group and years over 65, because the condition variables are used to define which condition is which. They don't count as predictors in the same way. In SAS, that predict statement, the analog is right here. Out PM is an option that generates a brand new data set. So the data set, I have given the name work.predFinal, meaning predictions from the final model. It automatically generates a column that it names pred, which is where I got the name from, of predicted outcomes. And then I correlate those predicted outcomes with the real ones down here. And so I showed the output for that specifically. It looks like around 60 to 70% of the variance in each of these response times is attributable to the difference between younger and older adults, as well as the slope for age in the older group. The other thing that I did in SAS that's different is I use, all of this, by the way, is margins in Stata. So Stata wins on that score. But I generated predicted means for every condition for younger adults and for older adults, and then I saved them to make a picture. So ODS right here, you may have seen this once or twice. That stands for Output Delivery System. What it does is save the table of estimates from the estimates commands into a data set that you can then read in and do math on or make pictures with. So here's the final model. We have the R matrix and the R correlation matrix across persons. Here's the fixed effects from the model. And if this were a normal class, I would have you guys volunteer for these things. But I don't think I have the bandwidth for this. The estimates then for all the simple effects and for the means, then here are all of the means. I saved those extracted condition variables from this label right here and then fed it into a picture. And here is, stop, my picture, my three-way interaction. So we have the slope of the lines conveys the effect of meaningfulness to driving. So on the left-hand side are the means in log response time for the younger adults. The right-hand side is for the older adults. And the slope of these lines going down means that the changes that are more meaningful to driving were detected more quickly. Response time is smaller in those cases. The difference in the slopes within a panel here is the interaction of meaning with salience. So if salience is low, which is the blue line here in the younger group, then meaningfulness to driving has a bigger effect on response time than if salience is high. Like if the change is already obvious, it doesn't really matter if it's relevant or not because it's obvious. So the effect of meaning is significantly reduced in the younger adults. So there is a significant two-way interaction in this panel, but there is not a significant two-way interaction in the older adults. They're slower across the board, so that's why their response times are up here. But in terms of the effects of the condition manipulations, the effect of meaningfulness is reduced in the low condition, but it's a little bit higher than the one in the older adults, or younger adults, excuse me, in the high salience condition. And this picture over here suggests that modeling log response time worked in the sense that the residuals collectively stacked in the one column appear pretty normal, and if you run it separately across conditions, you see that there's no evidence of over-dispersion. So this is about the most normal picture of real data I've ever seen. And of course, words. Lots and lots of words. So I describe sort of the setup, and then described the fitting of the alternative covariance structures, the different R matrices, and then talked about, just in general terms, what the simple effects were, because I would give a table that has all of those things instead. And so here's all of the different simple effects that I asked for, as well as the simple two-way interactions between meaning and salience within each age group. Okay. Do you guys want to go through the coefficients? Do you think that would be helpful or useful? Yes? One vote from Jing? Another? We're voting? Okay. Do you want me to do them, or do you want to take turns doing them? How do you want to play this? You do them, please. Hey, I have a PhD already. Okay, you're getting your money's worth today. What's SOS mean? Oh, that's like old school SOS. I thought that was a new one that I hadn't heard. Okay. SOS, please someone help me. It's not healthy for me to feel this way. That one? Okay. Thank you. Yeah, we're getting our dance on. Coronavirus be damned. I am still going to sing off key to my classes. It's my right as an American citizen. All right. Beta 0, here's my intercept. My reference point for the model. So that is going to be log response time when meaningfulness is low, which is what 0 means. Salience is low. And old group is 1. Okay, we got that far, right? Okay. Simple effect, because meaning is involved in a bunch of interaction terms. So if I scroll through the list here, keep track of everything I'm going to have to condition on. So this means that it's the difference between low and high meaning, specifically when salience is 0 and old is 0. So this is low versus high meaning when salience is low and old is, hang on, this was wrong. Old is 0. Younger adults are my reference point. Likewise, if I go for the main effect of salience, that's my simple main effect of low versus high salience when meaning equals low and old equals 0. I'm going to do YA for younger adult just to be a little bit more transparent. Okay, good so far? Now I have Rihanna in my head. Da 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 da. Yeah. All right. Two-way interaction term. Let's do the effective meaning moderated by. Nope. Hang on. There's that one and that one. Okay. So the effective meaningfulness when for low salience is negative. That's the minus 0.26 there. What does it become in the high salience condition? Which pattern is this? And you can hold up your fingers, okay? 1 for more positive, 2 for less positive, 3 for more negative, and 4 for less negative. We'll take a vote. Okay, survey says we've got some 4s rolling in from the shy people, or the people without cameras. 4s, everyone's voting for? Yes, this is a less negative. Indeed. So that means the effect of meaningfulness is weaker, is reduced, is mitigated, whatever GRE word you'd like to put there. So this is reduction in low versus high meaningful effect when salience is high. Am I done typing? Or do I need to keep going? Keep going? And we're talking about younger adults. So everything that we've got so far here is filling in that 2x2 table of means for the younger group specifically. It's giving me one simple effective meaning, one simple effective salience, and saying how those simple effects change in the high condition of each variable. I could also flip this around rather than talking about the effect of meaningfulness. I could talk about the effect of salience. So there's my salience effect in the low meaning condition. There's my interaction term. And it's the same pattern. It's a less negative, a weaker. So you could say it's the reduction in the low versus high salience effect when meaning is high and old is younger adults. Okay. With me so far? All right. Now, looking at my clock to make sure we don't overrun the class here. Main effect of old. So here's old. That's the difference between the younger and older groups, but I have to condition it on all the other interaction terms. So this is why younger adults versus older adults. It's a common abbreviation in the aging world that I used to be a part of. When meaningfulness is low and salience is low. Then this one, do you want to do, let's do old as the modifier. So we got these two to contend with right here. So the meaningful effect when it's low salience is negative. In older adults, this is the same pattern of less negative. So we have, I'm going to borrow some text here, I think. Reduction in low versus high meaningful effect when old equals old A and salience equals high still. Salience effect here, salience by old, same pattern. So I'll steal that. Salience. There we go. And meaningfulness is high. And now the three-way interaction. Dun dun dun. Okay. So two-way interactions take their constituent main effects and they make them one of the four trends. More positive, less positive, more negative, less negative. Three-way interactions take their constituent two-way interactions and do the same thing. So I'm going to go two-way interaction. Yeah, please. Because these old by meaning and old by salience are conditional on this three-way interaction right here. And so those two ways are when the third variable is 0. Let me put the parentheses on this one to make the same parallel. Can you repeat that, please? Oh, because I typed it wrong. That's why. Thank you. And this is why I don't do things on the fly very often. Thank you. Yes. Is that better? Yes. Thank you. I could pretend that I did that on purpose for pedagogical reasons, but you all know better. All right. So here's my, let's go that way for the three-way. Okay. So the meaning by salience interaction in the younger adults means that meaningful changes, the advantage for meaningful changes is reduced if they're visually conspicuous. That's what that means. The effective meaning is reduced in salient changes. When salience is high, you don't need meaning as much. That's what that interaction means. It becomes, I'm going to say, less positive and into the negative side, but probably still functionally zero in older adults. So putting it together, let's see if I can fit all this in one line. The extent to which, that's a good way to start off a two-way interaction sentence. The extent to which high salience reduces the effect of meaning in younger adults is reduced in older adults. Almost got it on one line. That's my three-way interaction. I could talk about it in three different ways. That's the way that I think lends itself to most directly. I could also say the same thing, the extent to which the effect of high meaning reduces the effect of high salience is reduced in older adults. So there's not as much of a trade-off between these two variables in older adults. And rather than trying to walk your reader through every possible simple effect, this is where you say, see figure 1. And you point and you give them something that looks hopefully a little nicer than that, but that has basic characteristics. So the trade-off in terms of the effect of meaning being reduced by salience, that in the younger group, the fact that the lines are less parallel. They're more parallel in the older group. That's the three-way interaction. Whew, that was tiring, but fun. All right, let me go back to that. Last one. I forgot the very last main effect. There's one more. Years over 65. For every year older than 65 in the older adults, log RT, what's my coefficient, goes up. Is higher by that. And that's all I have to say. I don't have to say in which condition, because years over 65 is a main effect. It applies equally across conditions, and I know that because in the previous model I had asked whether or not it needed to be part of interactions with meaning and salience, and the data said no. So yes, the older you are, the slower you are, equally so across conditions. There's the last one. Okay. So we've done one example so far. I have lots of examples planned for multivariate models. This is probably the only instance, this type of design, where the way that you would set it up is almost universal. Because the conditions are arranged such that they form this 2x2 combination, the parameterization of the model, meaning how you decide to set it up, let me go back to the equation here for a second, it lends itself to the same type of setup that we've seen where there's an intercept, and then you have main effects of your predictors, and then you have interaction terms. I can't think of an instance in which you wouldn't do it this way for this kind of problem. The next example that I have to show you is a triadic data example of 3 responses from the same family. I have a mom response, a dad response, and a response from an adult child. There are 2 different ways that you would want to set up a model like that. And so that's where we'll start next time, is trying to explain what those different ways are and what the model tells you. Because one of those ways is less intuitive and typical in univariate software, but it lends itself much more nicely to multivariate models and path analysis. And so we'll be turning the corner in terms of types of models that you will have seen with respect to fixed effects. So that's the exciting next step, example 4B and the rest of lecture 4 to go with it. Cool? All right. Any questions on this example before we call it good or otherwise? Okay, everyone's quiet. Well, I just want to say thank you for making the time to come and sit in this class. I can't even imagine how bored I would be if I just had to like sit and talk this stuff at my computer and not have at least some of your faces or your comments and questions back to me. So I know this is weird and uncomfortable and never ending, and at least for 4 hours on Tuesdays and Thursdays I get to feel normal. Like life is normal again, even though it's not. Like so, and you guys are the reason why. So I just want to say thank you for making time to be here and making the effort to keep this stuff going. So, shall we call it a day? All right, thank you guys, and stay safe. And I shall see you Thursday. Bye bye.